Welcome, everyone. It's my honor and privilege to introduce you today our speaker, seminar speaker, Professor Robert Nerem from Georgia Tech. Professor Nerem actually has connections to Ohio State, very strong connections. He earned his MS and PhD from the Department of Aeronautical and Astronautical Engineering, which, as you may know, merged with the Department of Mechanical Engineering in 2010 and is now joined with the Department of Mechanical and Aerospace Engineering. He then joined the Department of Aeronautics and Astronautics as a tenure-track faculty member, became full professor, and then served as the Associate Dean for Research in our graduate school. He then went on to become Professor and Chair of Mechanical Engineering at the Department at the University of Houston, and joined Georgia Tech as Parker H. Pettit Distinguished Chair for Engineering and Medicine. Petit. So it is French. Sorry. Minus the E. Parker H. Petit.
I'm just a petit professor.
Got it. Professor Nerem, to some of you who may not know, is an accomplished leader in biomedical research and has provided the fundamental framework for creating an interdisciplinary research culture both at the University of Houston and Georgia Tech. He was the founding director of Georgia Tech's Parker H. Pettit Institute for Bioengineering and Bioscience, and he served as the director of the Georgia Tech Emory Center for the Engineering of Living Tissues for 11 years. Dr. Nerem is also the founding president and a fellow of the American Institute for Medical and Biological Engineering. And among the numerous awards and honors he's received, he was elected to the National Academy of Engineering in 1988. He's not just in town for today's seminar. His pioneering spirit and outstanding leadership have earned him the College of Engineering's 2017 Lifetime Achievement Award for leadership, which you'll be receiving this evening. This award recognizes alumni who have demonstrated ingenuity, creativity, and dedication in improving our world. Please join me in warmly welcoming Professor Bob Nerem.
Well, thank you, Vish. It does get a little confusing because another name at Georgia Tech is Pettit. Joe Pettit had come from Stanford to be the president of Georgia Tech and made enormous contributions, but then Parker H. Petit also made enormous contributions, being a generous donor. And sometimes generous donors are more important than presidents of the university. So, but a pleasure to be here, a pleasure to have this opportunity to talk about, in a sense, what I've tried to weave into this talk is my sort of history and some of the things that I think are important in bioengineering today. I have these rules of life, and which my students had me write down a few years ago, and one of them is you have to be prepared to give up the life you've planned in order to have the life that awaits you. And certainly when I was a PhD student, I did not plan to have the career I've had. It's been an amazing career, but it wasn't a career that was planned. So with that, let me, background as indicated, all my degrees, including my PhD, were in aeronautical and aerospace engineering. My dissertation was carried out using a shock tube, actually an arc-driven shock tube, to study heat transfer, in particular radiation heat transfer in high temperature gases. This was a shock tube which basically could heat air to about 15,000 degrees Kelvin and simulated the atmosphere that would be created on a re-entry from a Mars mission. And when I started my academic career at The Ohio State University, my research continued to be focused on heat transfer in high temperature gases. There you see a picture of the shock wave. The shock has gone over this model representing what a reentry vehicle might look like. And again, those gases are 15,000 degrees Kelvin and allowed us to study radiation heat transfer. Now, the transition to biomedical engineering. At Ohio State, part of my research support came from NASA. And one day I got a call from NASA saying, Bob, we need your help. And I said, well, what do you mean? Well, we have a terrible vibration problem on the launch vehicle for the Apollo program. And we've just given Ohio State's College of Medicine a pot full of money to study vibration effects on human physiology. I said, well, that makes sense, but why are you calling me? Well, the people in medicine don't know anything about launch and reentry. I said, well, that may be true, but I don't know anything about biology and medicine. That's okay. We want you to be a consultant to this project. I said, okay. Fact of the matter is, this project was a window in a whole new world. And like most consultants, I made no contribution at all. So, I say little if any contribution, but I would really say no contribution at all. But a window in a whole new world. So, I decided, this was late 60s, and I decided in 1970 I should go over to Imperial College London because there was a very interesting group that had been organized there by a famous mathematician, a guy by the name of James Lighton. And he had put together a combination of clinicians, life scientists, engineers, mathematicians, computational scientists to study cardiovascular disease. And I spent the better part of the year there and came back at the end of the year, and as you can see in that last bullet, what I worked on there was basically turbulence in the aorta and transport in blood vessels. And by transport, I mean transport between blood and the arterial wall. In other words, across the vascular endothelium. Now, returning to Ohio State, I made the decision to phase out my shock tube research and transition into biomedical research. My formal engineering education had prepared me in part for biomedical research. I really did have an excellent engineering background, but I had a limited knowledge of biology and physiology. I thus was fortunate to have the opportunity to move my research to the Department of Veterinary Physiology and Pharmacology. And this is all to someone who's sitting in the room here today, Professor Robert Hamlin. Bob, raise your hand so people can see who you are. I'd befriended him, and he called me one day, I think it was probably December 1970, and said, Bob, do I have a deal for you? Well, I knew him enough to wonder what, in fact, a deal might be. He said, you want to move into biomedical research? That's what you're doing. You're taking on new students doing bioengineering. My proposal is that you move over here to veterinary physiology. You and I will share my office. Your students will share the lab with my students. We will teach you and your students physiology. And you will teach us how engineering can be better used to understand physiology. This is like December 1970. Talk about someone who had a vision, because that was certainly off the charts in terms of the way research was being conducted back then. And Bob, I owe you a great debt and thanks. So I put on this slide my early mentors. I don't think I'm going to see John Lee today. He's retired, but although still active, as I understand it. He was my PhD advisor at OSU and for my shock tube research. Then there was Colin Caro. He was my main collaborator at Imperial College London. Then there was Garvin von Eschen. That's another important anecdote. Because I came back from Imperial College, and Garvin wanted to know, he was chair of aeronautical and astronautical engineering. He wanted to know, what do you want to do now? Well, I had a lot of grant support for my fluid mechanics heat transfer research, had a big research group, and I said, well, Garvin, I think what I want to do is phase out all this research I've been doing and go into biomedical research. And he looked at me and he said, Bob, if that's what you have a passion to do, then that's what you better do. And so that freed me up to move into the biomedical world. And again, Bob Hamlin, Robert Hamlin, a professor of veterinary physiology and pharmacology, provided the opportunity to immerse myself in learning about the life sciences. Early research was focused on the role of hemodynamics in the atherosclerosis. This led me to the study of the vascular endothelium, that inner lining of cells in a blood vessel that's exposed to blood flow and the physical forces imposed. And to understand vascular endothelial cell biology, one must understand the interaction between the chemical biological environment and the physical environment. So much of my early work was actually in that area. This slide here shows data from, let's say, 45 years ago. Two things, and I really should start on this slide first. We were interested in how the endothelial morphology might in some way reflect the flow environment that was taking place. Because certain parts of a bifurcation, cells became more rounded, other parts they were highly elongated, more rounded here where there seemed to be a separation of flow. And here you see different pictures showing these different types of endothelial morphology. That ultimately led to us doing in vitro studies, studying the vascular endothelium under flow conditions, cultured vascular endothelial cells under flow conditions. Here you see vascular endothelial cells that are not exposed to flow, and here you see them being exposed to flow. So in fact, there was a reflection of the flow environment in terms of the morphology of the vascular endothelial cells. Now, I titled this slide, Fast Forward to Tissue Engineering. Prior to 1950, references to the concept of tissue engineering and regenerative medicine may be found in the literature. That may surprise some of you, but this whole idea of being able to create tissues out of living cells for implantation, to foster repair and regeneration, those ideas go back quite a ways, as I'll show you in a minute. The 1970s, 1980s, research on what was called tissue engineering emerged. And it was in 1987 that the term tissue engineering was actually coined. However, by the mid-1990s, the term regenerative medicine began to be used. But what is meant is the replacement, repair, and/or regeneration of tissues and organs. Now I show this. Most of you probably don't know who Alexis Carrel is, but you probably know who Charles Lindbergh is, of transatlantic flight fame. After his flying days, he became interested in the biomedical world. Alexis Carrel was a well-renowned biomedical scientist, and they wrote this book, The Culture of Organs, published in 1938. 1938, that's what, 80 years ago? And they laid out some of the concepts that became inherent in the whole world of tissue engineering and regenerative medicine. The first meeting that was held, called Tissue Engineering, was 1988 at Lake Tahoe, California. These were the editors, Richard Skalak and Fred Fox, and I think, Vish, you were an undergraduate student in a class of Richard Skalak. Small world, right? And then the field moved forward. I show this simply to show what we're talking about. Here, and this is a relatively old slide, but one of the early tissues made was skin. And in particular, in this particular case, the company making this, advanced tissue scientists, made a dermagraft, not a full skin, but just a dermagraft. So what you see here is, in this picture on your left, the face of a German lumberjack after his face had met up with a chainsaw. Not the best experience, obviously. Here is his face being pieced back together using this dermagraft, this skin substitute made out of dermal fibroblasts. And here you see his face 6 months later. Yes, there's a hint of a scar, but to think that using the biological mechanism of fostering repair with this skin substitute, one could, oops, is not what I wanted to do. Oh, here we go. Well, to go from this to this in 6 months shows the power of being able to harness the biology of the human body. So, some of the products in the market in terms of tissue engineering, yes, there's the skin substitutes. There's also Medtronic's infused bone graft for use in spinal surgery. Another example is the Matrix SIS standing for small intestine submucosa. More than 2 million patients have been treated, and applications include the rotator cuff and hernia repair. What are some of the advances that are envisioned? Certainly, blood cells derived from stem cells, thus reducing the need for blood donors. An insulin-secreting, glucose-responsive bioartificial pancreas. Heart valves that, when implanted into an infant, grow as the child grows. In today's world, if you have a child with a defective heart valve, yes, you can do a replacement, but every few years, there's going to have to be a new replacement as the child grows. Yet, if you had a heart valve made out of living cells that would grow with the child, you wouldn't have to have this continuous surgeries. Then there's cell-based therapies for the myocardium, and probably the holy grail is repair and regeneration of the central nervous system. That if I was a young person today entering the field of bioengineering, it's the neural area that I would want to focus on, because I think that is in many ways the holy grail. Here, and this slide is a few years old, but it makes a point. Looking at what's happening in different areas as we move from R&D to preclinical work to phase 1 clinical trials, phase 2 clinical trials, phase 3 clinical trials, and then approved by FDA to go on the market. And these are different applications. Each of these points represents something going on in industry. So it's a very active industry, although if you look what's actually out there in terms of what's on the market, a relatively small number of points. But at the same time, clearly in the orthopedic area, a number of things moving along. Skin, that's where we have a lot of products out there. Vascular, yes, a lot of things moving along, but a long ways to go. And there probably should be a few more data points today. The neuro area, a lot of things that are in play, and then other. But I think the important point is that we're not just talking about academic research. We're talking about this getting translated in a way as to help patients. And that means moving things out from university research laboratories into companies. And as you can see, a lot of things are in process. Stem cells, that's something I got into. If I was going to try to tissue engineer a blood vessel to use for example, bypass surgery, I needed a good cell source, and stem cells seem to be the appropriate vehicle. Of course, embryonic stem cells. There's also adult stem cells. I think more important is the induced pluripotent stem cells, where one can take, and this was discovered by a Japanese scientist, one could take skin fibroblasts and back them up into a stem cell, and then use that to derive most of the cells that you need. And of course, there are also progenitor cells. But this is certainly an important part of the future of where we're going to get cells for what we want to do in the way of tissue engineering, regenerative medicine, and cell-based therapies. Approaches of stem cells, source for in vitro fabrication of cell-based constructs for implantation to replace disease-injured tissues and organs, replacement of cells to induce the repair of disease-injured tissues and organs, the development of a cell factory for the production of stem cell secreted factors needed for repair. You know, if we really knew the signals that would drive repair and regeneration, we could introduce those signals without actually introducing the cells themselves. We would find ways to deliver those signals in order to foster repair and regeneration. And then the other thing I have up here is the development of organs on a chip for use in drug discovery as an example. This is simply a picture to highlight the work going on organs on a chip. In this case, it's called human on a chip. The hope is to integrate at least 10 different organ on a chip devices into a system that mimics the human body. So far, people have been able to put together maybe 4 different organs on a chip in order to simulate what goes on in the human body. But clearly, we're going to have to do more than that. But this is definitely making progress. And if we really had this kind of an in vitro system, as I mentioned in the previous slide, to use in drug discovery, it would greatly cut down the use of animal studies. The fact of the matter is, although we do animal studies, we're required to do animal studies by FDA, animals are not necessarily a good replica of what's going to go on in the human system. So we would much rather have this kind of a human on a chip representation to understand how a drug is going to affect a human being. In terms of the stem cell market, this shows for 2020, $8 billion market. It's probably going to be more than that. And different applications, orthopedic, a lot of applications there, but also the neural area, cardiovascular area, and the inflammatory approaches, diabetes therapy. So there's a lot to be done with stem cells. And again, because of advances, we no longer have to talk about embryonic stem cells because we're going to be able to do this with induced pluripotent stem cells. The global market, certainly cell-based therapies, is the fastest growing segment of the regenerative medicine and also the largest segment. Stem cell therapy market predicted to be 40 billion by 2020, 180 billion by 2030, and the T-cell therapy market could be worth 30 billion by 2030. Currently in the U.S., 2,000 active stem cell and 200 cell immunotherapy clinical trials. So a lot taking place, but still a long ways to go. I put this in simply to highlight the following. When it comes to what's been approved by FDA, a very small number of stem cell treatments. The vast majority of stem cell procedures being conducted in clinics not approved. You may see advertisements and so forth. Most of these are not approved by FDA, and that really means that insurance companies are not going to cover it. On the other hand, if you're a patient in need and there's seemingly no available treatment and stem cells offer a possibility, at least if you have the resources, you're willing to pay that in order to see if it can help you. Also, as indicated here, that 2/3 of these situations offer procedures involving stem cells derived from the patient, him or herself, and these are what we call autologous in nature, and a variety of conditions for where these unapproved treatments are being used. Now, I highlight this slide, stem cell-based therapies could be revolutionary, provide cures for chronic incurable disease, the potential for reduction in long-term healthcare costs, benefits for the economy. But the promise and impact of stem cell therapy, although clear, question is, can that promise be fulfilled for tens of millions of patients? So, a lot of my interest in recent years has been, how does one go from benchtop research to having what one needs to actually treat patients, these cellular therapies. You need to scale up to have enough cells, you need to have quantitative systematic approaches, you need quality control. This is all going to be important. Yes, benchtop research is critical, we need to learn more, and yet we need to figure out how to move these forward to ultimately be available for the treatment of patients. Now here, as I headline this slide, the fundamental challenge is in the biomanufacturing of therapeutic cells. This is a critical issue. Cells can undergo subtle and often rapid phenotypic changes due to variations in culture conditions. Cells used for therapeutic purposes can be highly dependent on the processing they have undergone. And the challenge is to develop the tools, technologies needed for well-characterized, quality-controlled, and highly reproducible manufacturing process. So this has led to Georgia Tech's cell manufacturing initiative. It started, I say 2010, but actually started with a one-day workshop in 2008 on cell manufacturing. This led to being awarded a training grant from the National Science Foundation on stem cell biomanufacturing. This led to creating a short course, first held in 2013, on regenerative medicine manufacturing, first held in Portugal. Then we hosted it in the US in 2016, and we'll be back in Portugal in 2018. And in 2014, the U.S. National Institute for Standards and Technology, NIST, awarded a grant to Georgia to develop a technology roadmap for cell manufacturing. And this roadmap allowed us to take the next really major step forward. 2015, we were fortunate enough to have the Marcus Foundation award close to $17 million to establish the Marcus Center for Therapeutic Cell Characterization and Manufacturing. And creating this center then led to an award to the Marcus Center of an Engineering Research Center on Cell Manufacturing. That's from NSF. And 2017, Georgia Tech also is a partner in several other efforts as part of the Manufacturing USA initiative. Now I mention this because, the first workshop, a one-day workshop in 2008, and finally 9 years later, in 2017, we get an Engineering Research Center award. So you have to figure out what as an institution you really want to do, and then move forward step by step. I'll pass that slide. In terms of the cell manufacturing technology roadmap, that resulted in also creating a consortium. And the most important thing on this slide is to show that what we've developed at Georgia Tech This consortium that developed the roadmap involved 16 universities, 30-plus companies, FDA, Department of Defense, NIH, NSF, NIST, all working together for national workshop, really industry-driven, because it would not be appropriate for a bunch of academics to tell industry what they need. What we need is for industry to tell us, and then we execute a plan to develop those technologies and those tools. These are the deliverables for the consortium. Create a national consortium for stakeholders involved in cell manufacturing, bring industry, academia, government agencies together to identify barriers, impeding progress, critical R&D directions, write the roadmap for technological innovations involving the stakeholders, the entire cell manufacturing value chain, and in the process, hopefully, accelerate the translation of cell and cell-derived products to the healthcare market. Get a cough drop out for a minute. And this again shows the combination of groups in this consortium. Again, industry, clinical, GMP facilities, government agencies, private foundations, and academic research. And this is a picture of the technology roadmap, and you can go online and download this technology roadmap if you're interested in the details of it. Priority challenges and needs coming out of this roadmap: cell characterization, cell culturing processing, process monitoring and quality control, cell preservation, distribution and handling, standardization and regulatory support, and workshop development. And just a little bit about each of these in terms of cell characterization. Develop online in-process characterization for predicting cell function. Develop advanced integrated in-process sensors that can non-destructively gather and transmit data. Develop reliable, real-time image-based inline analytical methods. Develop standardized high-throughput assays to ensure cell-to-cell consistency in terms of phenotype functionality, quality, and potency. In terms of cell processing, just to hit a few high points: advanced high-throughput image analysis and integrated data capture technology. Develop and optimize inexpensive chemically defined media and universal feeder systems free of animal cells and components. Engineers bioreactors with increased capacity and integrated information technology. And develop automated closed systems that will allow for parallel manufacturing of multiple patients' samples. A critical issue is scale up, how to go from the number of cells you have in a laboratory to what you need for a patient treatment. And you can't simply scale up a T-flask. That doesn't get you anywhere. So, as indicated here, we've got a few problems going from lab scale up to full-scale commercial. Yes, there are a few problems. And when we talk about scaling, sometimes we talk about scale out and sometimes scale up. Scale need not necessarily imply scale up, but instead scale up, producing multiple individualized products in parallel. Scale out would be for indications where you have low doses and a small patient population. Scale up for indications with high doses and a large patient population. The whole issue of cell preservation and distribution, and I'm not going to go over this in any detail. The standardization and regulations, there really aren't standards yet for the cell therapy industry. That needs to take place. And as part of that, we need to establish regulatory standards to ensure consistency of materials from different suppliers. The center we now have, by the way, it does cell characterization for 3 different medical schools that are doing clinical trials. Case Western University, Duke University, and University of Miami School of Medicine. All are using mesenchymal stem cells, but when you characterize the cell populations they're using, each of the 3 are different. And Bernie Marcus, who funded our center before we got the Engineering Research Center, he was one of the co-founders of Home Depot. He's the kind of donor that's very interesting. He doesn't want his name on a building. He wants his money to go to actually see things happen. And so his money is going to support these clinical trials as well as support the Georgia Tech effort to be of assistance to these medical centers. And then there's workforce development. I mentioned earlier the short course that first held in Portugal and then in 2016 in the U.S. Training programs for PhD students and postdocs that include internships in industry, and a continuing education for the retraining of existing workforce that needs to be involved, and this might come from technical colleges. It's one thing to talk about training people at the PhD level, but you also have to train people that are going to be at the working level down where the manufacturing is actually taking place. And this is simply the short course held at Hilton Head March 2016. Next one is to be in Portugal in 2018. So I mentioned Bernie Marcus, and he provided basically $17 million to establish the Marcus Center for Therapeutic Cell Characterization and Manufacturing. The vision is to bring together bioengineers, manufacturing engineers, industrial engineers to work closely with cell biologists, clinicians, and industry to advance cell therapies for broad clinical use. And the focus of the Marcus Center is on the development of tools and technologies needed for the development of well-characterized, quality control, efficient, and highly reproducible manufacturing processes. I'm not going to say a whole lot about this slide. Again, key goal of the Marcus Center is to establish a world-class infrastructure to facilitate the characterization and manufacture of therapeutic cells. An initial $23 million investment from the Marcus Foundation, from what we call in Georgia the Georgia Research Alliance, and from Georgia Tech. And the Georgia Tech amount includes $5 million for new faculty hiring. So, out of all this came the award of the Engineering Research Center from NSF on cell manufacturing, what we call CMAP, cell manufacturing technology. And you can see what the goal of this center is: to develop new engineering tools, scalable methods to better characterize, expand, differentiate, separate, transport, and store high-quality cells so as to provide consistent therapeutic effects. Tech is the lead institution, with primary partners being University of Wisconsin, the University of Georgia, and the University of Puerto Rico, and we also have international partners, CCRM in Toronto, and Curram in Northern Ireland, in Ireland, not Northern Ireland, in Ireland at Galway, and Osaka University in Japan. And this simply lays out what's going to happen in this center in terms of test beds. Test bed 1 is the MSCs for regenerative medicine. Test bed 2, therapeutic T cells for T cell immunotherapy, and test bed 3, these iPS cells for cardiomyocytes for repair of a damaged heart. I don't think I should go over all the details of this slide. So, when we talk about cell therapies, new technologies, yes, they tell an impressive story. The clinical community is receptive. Manufacturing issues are beginning to be addressed. And improvements in the regulatory process and reimbursement have the potential to accelerate the pace of innovation. There are a lot of things that need to be done in terms of the regulatory process and the reimbursement process. As I mentioned earlier, I believe the holy grail is really neurodegenerative diseases, disorders, repair and regeneration of the central nervous system. With an aging population, the threat of a tsunami of neural disorders. And one example is Parkinson's disease. With 5 million people worldwide suffering, more than 45 million people living with dementia in the world. And those numbers are just going to dramatically increase as we move forward. So, the promise of neurotechnologies. And I put this slide in because we will need not only experiments, not only practical engineering, we will also need computational approaches. These biological systems are so complex, and you're never going to be able to design an experiment that covers all the options. If from your experiments you can develop a computational model, and you will see how that model agrees with your experiments, that will then lead you to new experiments, that will lead you to improvements in the computational model, and that will lead to further improvements in the experiments. So it really has to be a combination of experimental and computational approaches. In the U.S., many states, worldwide, many countries are focused on the translation of stem cell therapies to patients. But as I indicate in this slide, the optimal word is not simply patients, it's having patience. Because these things take time. The time to go from benchtop to the clinic can be quite long. And certainly bringing a disruptive technology to the market takes a while and requires very much patience. Now, in 1994, that's 23 years ago, I was interviewed by U.S. News and World Report, and I made the comment that biology was too important to be left to the biologists. Excuse me. Now, my biology friends said, "Bob, what are you saying? Are you putting down biologists?" I said, "No, on the contrary. I think you biologists have taken the field to a new level, and you are to be congratulated on that. But it's a new level where other disciplines can now contribute, and everything can move forward." It's very interesting. Not too many years ago, there was a report out of the National Academies, and I may have a slide on that. Let's see what's next. Yeah, here it is. New Biology for the 21st Century. The essence of the new biology is the integration of many subdisciplines of biology and the integration into biology of physicists, chemists, computer scientists, engineers, mathematicians to create a research community that can tackle a broad range of scientific and societal problems. Bringing these disciplines together as an interdisciplinary effort, this scientific integration will lead to deeper understanding of biological systems. And that will lead to our really being able to provide solutions to societal problems in the health area, but also in environment and energy and food. So the future is really creating these interdisciplinary teams. I titled the slide "Building a Better Understanding of Biology," and it's sort of picking up on the same theme. We need to understand quantitatively the relationship between elements of complex biological systems. That means that we need to integrate our knowledge across the biological scales. We need to have a predictive ability. And this will require models that drive the design of new experiments, that in turn will drive the advancement of new computational models. This is sort of what I said a few minutes ago. This is maybe a better way to say it. This is a slide I've always liked. You see here a father with a small son looking at this monument showing these 5 people. And the father says to the little boy, "There are no great men, my boy, only great committees." Well, if you've been in academia for a while, you're not sure about great committees. But certainly, it's going to be great teams. And engineers have an important role to play in these great teams. Some final thoughts. Be open in the widest possible way to encountering a new person, a Bob Hanlon who might come into your life, to a new opportunity, as these represent new teachers and new learning experiences. If you encounter a closed door, and for all my success, I've encountered a lot of closed doors. Simply look for another door that might be open. Don't waste time on a door which is closed. And be willing to let go of the life that you had planned, so as to have the life that awaits you. Certainly, as I think I indicated earlier, I never thought my life was going to be what it turned out to be. I was going to do aerospace engineering research, and I was going to become a full professor in aerospace engineering, and that's what I would be doing. Maybe I would be working on a Mars mission. Well, I never worked on the Mars mission after my PhD, and then my heat transfer in the shock tube was funded on the basis of a potential Mars mission. But I went in a different direction. And I've been very fortunate to have a variety of people in my life who have mentored me and have contributed to the change in my thinking that had to take place for me to move forward with the career I've had. And this is my final slide. I call it Doing the Impossible. From Robert Goddard. Robert Goddard was a famous rocket scientist back in the 1920s. And he said the following: "It's difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow." Well, for all you young people in the audience, you are not only the hope of tomorrow, today you're the hope of tomorrow, and you will create the reality of tomorrow. And I just wish you the very best as you move your careers forward. And I can only hope that you will have as great a ride in life as I have had. Thank you very much.
We have time for questions.
Thank you both. We enjoyed your talk. I wanted to ask about the Marcus Center. I understood that you're trying to manufacture and scale up and translate the stem cells, and then you collaborate with the clinics. However, best would be if these cells are autologous. So do they send you patients, even for the induced pluripotent stem cells? I mean, you still need skin fibroblasts. So do you get cells from them, then you expand, characterize, and then you send back, or how does it work?
We characterize the cells that they are using. And yes, many of the treatments involve autologous cells, but the real future is with allogeneic cells. That's where you really have the opportunity to make an impact. But again, you know, when 3 different medical schools do ostensibly the same clinical trial, and they get slightly different results, and it turns out, well, their cells were not exactly the same. Yes, they were mesenchymal stem cells, but they weren't exactly the same. I think it's important to know what is the characteristics of the cells we're using for any cell therapy. And that's what the Marcus Center is trying to help with.
And I have a second question. I was curious, what is the relationship now of the Marcus Center with the Petit Center that was doing the mechanobiology and the mechanical?
The Marcus Center is a center within the Petit Institute for Bioengineering and Bioscience.
Thank you.
I had one. In a lot of the generation or regeneration of tissue, there's attention paid to vascularization. Is there sufficient understanding of anervation at the same time of that tissue? Or is that not even a consideration right now? Because it's all homogeneous.
Certainly, I would not say it's not a consideration. It's an important consideration, but we just don't know enough. So yes, on the one hand, we have to move things forward from the benchtop into understanding what we can do in terms of clinical trials. At the same time, there needs to be real discovery science. The interesting thing about tissue engineering and regenerative medicine is that the basic biologists really haven't been involved to any great extent, and therefore, we don't have the fundamental basic biology knowledge that we need for a lot of things we're doing. So there's room for research, and all the way from the benchtop side, getting a better understanding of the basic biology to how do we translate this into patient treatments.
And the slide you showed of the patient with the chainsaw injury, the healing looked superb at 6 months. Did that patient have sensation in the healed tissue?
Yes.
It's interesting.
And it turns out, I mean, at the time, and I probably should have said this, the thought was, certainly the company's approach was, this is replacement tissue. But in fact, it was only there on a transitional basis, but allowed and fostered the patient to regrow its own skin. So, yes.
Thank you for the talk. So, the last point that you made was the future lies in using allogenic cells, like from a different host. So, while you're working with all these clinics, have you found a potential host of, or a potential source of cells that can scale that?
Well, we might go back to the IPS cells, the induced pluripotent cells, but not to use them one patient at a time. To use, by the way, these skin substitutes, they were using dermal fibroblasts from newborns. And they could take those dermal fibroblasts and expand them. Here you got a small population, expand it to a size that would cover an entire football field. That's the kind of now. So that skin substitute, the slide I showed about the German lumberjack, that was done with allogeneic cells. The cost saving will come from using allogeneic cells. If every patient is an N of 1, it's going to be an expensive proposition.